So as a quick reminder, there are exponent rules that we are going to use to help manipulate exponential functions. They're all exponents or exponentials, so these exponent rules apply. Let's talk about the product property. This is one of many exponent rules, but specifically one we need to remember today. It says that if you are multiplying bases together that have the same base, so notice it's b and b that have the same base, all you have to do is add those exponents. So multiplying bases means adding exponents. Does that sound familiar to us? So if we see in the example, you have x to the 5th times x to the 3rd. We would just add those together. That's x to the 8th. If we add 2 to the x times 2 to the 3rd, those bases match, so we still add the exponents. We just can't actually add x and 3 together, so we just leave it as x plus 3 in the exponent. Do we accept? Okay, second exponent property we're going to remember is the power property. The power property, it happens when you have a base with a power raised to another power. Base to a power raised to a power, that means you're going to multiply those powers together. So a power to a power means multiply. If you're remembering something that you probably used in your previous classes, these are your mad spam rules. I don't know if that acronym means anything to you, but these are your mad spam rules. So if we look in our examples, x to the 5th raised to the 3rd power is like x to the 5 times 3, which is x to the 15. And if one of those happens to be a variable, like 2 to the x raised to the 3rd, that's just 2 to the 3x. We're just multiplying those two things together. Yes? There are more exponent rules, but the third one we're going to go over today is your negative exponent rule. So we don't love having negative exponents shown in our final answer. So we like to clean them up. That's what I like to call it. But we will also use these within problems to be able to simplify things in different ways. But the negative exponent rule is basically that if you have a negative exponent, don't love that, you take the base and the power and you move it to an opposite side of a fraction and make the power positive. So it goes from being negative to positive when you switch the sides of a fraction bar, and vice versa. If it's negative in the bottom, you can move it up to the top and make it positive. So for example, if we have x to the negative 3 power, that's the same as 1 over x cubed. Do you see how it just moved down, became positive? And vice versa, even if the base is a number and the exponent is a variable, same thing works. So 2 to the negative x power is 1 over 2 to the x power. It just becomes positive. Do those look familiar to us? Okay, cool. Here's what's interesting though. Since we've been talking about exponential functions, we haven't really touched on transformations of these functions yet. We're going to do that today. But transformations of exponential functions are actually just manipulations of the exponents using exponent rules. So let's talk about some of our favorite kinds of transformations, that's sarcasm, our horizontal transformations. So we know our horizontal transformations are shifting the graphs left and right, as well as stretching them horizontally or shrinking them horizontally, or reflecting it over the y-axis. Those are our horizontal transformations we learned about in section 1.12. What we can do is we can actually look at these exponential functions and talk about their horizontal transformations, and eventually we're going to tie that back into what's happening with the exponents. So without getting too weird, we have f of x equal to 4 to the x plus 2 power. Compared to what would be the parent function or boring function, let's say we're comparing this to y equals 4 to the x, what kind of transformation occurred here if I put a plus 2 inside the function? Which direction is it translated? Plus 2 means, yes, it's going to go to the left, and it's going to go to the left 2 units. Okay, so quick reminder that our transformations, if you see plus 2 inside the function, inside in this case means in the exponent. It's going to move to the left. Okay, for question B, what kind of transformation has occurred if my regular function was y equals 2 to the x? It now says 2 to the 3x. So what have I done? Say again? Horizontal dilation by a factor of 1/3. Ooh, thank you for flipping that number over. Remember, horizontals are the weird ones. So it's going to be a horizontal dilation. In this class, you don't have to get specific if it's a stretch or a shrink. You're just going to call them dilation by a factor of 1/3. Again, the 1/3 comes from this 3 that is now in the exponent. Can you guys give me the answers for C and D? So identify first what the basic parent function would be. There's not an actual parent function for exponentials because the base will be different each time. But compared to a boring base version of it, what is happening in C and D? Give yourself a second. Okay, for number C, if we're comparing it to 9 to the x, what has happened here? A horizontal what? Dilation by a factor of what?
2.
Cool. By a factor of 2. Because technically it's multiplied by 1/2, so you use the reciprocal. And instead of 1/2, it would be 2. How about in D? What is happening there? If I compare k of x to the function y equal to 5 to the x, what is happening? Translation, definitely. What direction? Right. How many units? 1 unit. Cool, cool, cool. Let me make that one not look like an L. Here's what's really interesting about exponential functions and their horizontal transformations. If we look at example 1a, so we've already talked about the fact that it is a translation left 2 units. We could rewrite this property using the power property in reverse to not only show that it is a horizontal transformation, but there's actually an identical vertical transformation that does the same thing to the graph. What I mean by that is, if we use the power property backwards, we were adding these two numbers together. So if I undo that, that means we're multiplying 2 bases with those powers. Do we see how that happened? You had plus 2. That means we're multiplying 4 to the x times 4 to the 2. Okay, well, what's 4 to the 2 power? 16. Oh, look at that. That's a completely different function that's going to end up looking the exact same on my graph. They are equivalent. But this does not have a horizontal transformation anymore. What kind of transformation is that? It is a vertical dilation by a factor of 16. So weird. We are saying that a horizontal translation and a vertical dilation could end up being the same function. Weird. Here's our important idea for the front of our notes today. It says, we're going to put like little stars next to this because, yeah, this is important. Every horizontal translation of an exponential function when you have b to the x plus h is equivalent to a vertical dilation of the exponential function where a is exactly equal to b to the h power. Here's what I need you to highlight. A, the amount we're going to vertically dilate by, my initial value, if you will, is the same as b to the h power, what I am horizontally translating by, the h. So instead of telling me in the next couple problems what kind of horizontal transformation is occurring here, we're going to talk about what kind of vertical transformation is happening here. Here's how we do this. Really pretty simply, we can see that this is a horizontal translation to the left 3 units. We know that. But instead, let's write it like this. We could write this as 2 to the 3rd power times 2 to the x power. Where did I get those numbers from? Where did the 2 to the 3rd come from? The plus 3. So again, this number right here and this number are going to be the same. Well, what is 2 to the 3rd power? Don't say 6. 8. This is 8 times 2 to the x power, which means that instead of taking 2 to the x and horizontally translating it 3 units left, what kind of vertical dilation is this? Oh, I just said the answer. I was going to ask, what kind of transformation is this? This is a vertical dilation by a factor of 8. So those two transformations are identical or equivalent on this function. Okay, in part B, let's do the same thing. I can look at this and I can tell you right now, it's a horizontal translation to the right 2 units. Cool, but what's its vertical version? That means we're going to separate it using the product property into what 2 numbers? 3 to the something times 3 to the something. 3 to the what? -2. Okay, if you look at the one we just did, we did 2 to the 3 because of the plus 3, which means we're going to do this as 3 to the -2 times 3 to the what? X. Yes, I know I'm writing them in a different order. It's because our initial value goes first, a, b to the x, and I just like to get them in the correct order. So again, this is from here. Well, what is 3 to the -2? Good idea. Think back to the top of the paper. We have a negative exponent rule. What does that mean I can do with that negative exponent? Put it on the bottom. Okay, so this is 1 over 3 squared times 3 to the x. And what is 3 squared? 9. This is actually 1/9 times 3 to the x. What kind of transformation is that where there's a 1/9 in front of the function? It's a vertical dilation by a factor of 1/9. All right, in part C, this one's only different slightly. What's different from C compared to A and B? It already has a vertical dilation. We already have an initial value there, but no big deal. We're going to handle it. Not changing anything about what we've been doing. This is going to be 4 times 3 to some power times 3 to some power. What are those 2 powers? 3 to the what and 3 to the what? 3 to the 2 and 3 to the... Very good. Okay, and the 2 again comes from this plus 2. Okay, cool. Now I just need to simplify. PEMDAS tells me to do 3 to the 2nd power first. What's 3 squared? 9. And then I have a bunch of numbers I can multiply together. And by a bunch, I mean 2. You are not allowed to multiply by 3 to the x. That's a base with a power. It's protected by that exponent. But these 2 numbers right here are just numbers multiplied together. What's 9 times 4? 36. So this is 36 times 3 to the x. So we started with a vertical dilation by 4 and a horizontal translation left 2. We ended up with just a vertical dilation by a factor of 36. So we're able to manipulate these equations, not like we were able to manipulate polynomials by just straight up multiplying or anything. We have to use these exponent rules to manipulate them. But every translation horizontally is a vertical dilation. Let's talk about what happens when we do not just horizontal translations, come on, Miss Quigley, but in fact, what happens when we do horizontal dilations? What does that manipulate my equation to? I'm glad you asked. Flip your paper over. We're going to talk about it. So this is also pretty important. It doesn't have a box around it, but I would put like a bunch of highlights just like on the front side next to this right here. This is telling me that we can use the power property. That's the second property where you have multiplying means adding to show that every horizontal dilation of an exponential function is equivalent to changing the base of the exponential function. This is basically the only time you will ever change the base of an exponential. That's not something you will typically do unless you have a power to a power. It does change your base. So just like on the front, we're going to write each of the following exponential functions as a horizontal dilation. Oh, that's not what we're going to do. Those instructions are kind of weird. But anyways, for each, we're going to write an equivalent expression that represents the change of base in the exponential. Here's what I mean by this. If you notice that you have 2 to the 3x power, that means we employed the power property to do 2 to the 3rd power raised to the x power. Because 3 times x is 3x. So we see how we've just undone basically the power property. Well, what is 2 to the 3rd power? 8. So we are saying that these two expressions are exactly the same. They would graph the same function. So a horizontal translation is the same as a change in the base. Those were the wrong words. A horizontal dilation is the same as a change in the base. So translations are a vertical dilation. Horizontal dilations are changes of bases. Those were the right words to say out loud. Okay, well, what if we kind of make this a little more complicated? What if we have this kind of dilation by a factor of 2? What does that mean for my change of base? Okay, well, let me just separate these for a second. Basically, undo the power property. This is going to be 9 to some power raised to the x power. What is that power? 9 to what? It says x divided by 2. What number am I multiplying by? 1/2. So this is 9 to the 1/2 raised to the x power. Because 1/2 times x is 1/2 x, or x divided by 2. Okay, well, can we take 9 to the 1/2 power? Don't say 4.5. What is the 1/2 power telling me to do? Okay, here's an extra product or a power exponent rule that we've obviously forgotten. If you have a power or a base, raised to a fraction power, you would rewrite it as the nth root of a to the m, top in, bottom out. So the top number goes inside the radical, the bottom number becomes my index. So this 9 to the 1/2 is actually the square root of 9. The 2 and the 1 can be invisible because we don't ever show that index or power. So again, this is just like square root of 9 raised to the x power. Well, what's the square root of 9? Oh, what's the square root of 9, y'all? Okay, this is 3 to the x. So we are saying that a horizontal dilation by a factor of 2 is the same as changing the base to a 3. From 9 to 3. I want you to try C and D. D is going to be a stretch question, but I think you got it. And if you didn't remember this exponent property, write that one down for yourself. For C, I think C is really accessible. D might have stumped you for a second. But if we were to rewrite this, undoing the power property, this would be 3 to the 5th power, all raised to the x power. What is 3 to the 5th power? Don't say 15. 243 raised to the x power. So that is saying that for the function 3 to the x, a dilation horizontally by 1/5 is the same as changing the base to 243. For the this is the fourth one. For part D, if we rewrote this, undoing the power property, we would have 1/2 raised to the negative 1 power to the x power. That's a whole lot of gross, so let's fix this. One of the things about fractions and powers we might have forgotten is that this power that you are raising a fraction to will actually go to both the number in the top and the number in the bottom. So we are saying, in fact, that this is 1 to the negative 1 power over 2 to the negative 1 power, all raised to the x power. Okay, gross, don't love that there are negative exponents there. How do I get rid of negative exponents? You flip it to the top. If I move the 2 to the 1 to the top, it just becomes a 2. If I move the 1 to the negative 1 to the bottom, there's a 1 in the bottom of the denominator. I don't need to show. So this is really just 2 to the x power. So taking the exponential 1/2 to the x and reflecting it over the y-axis is like doing 2 to the x power. We've changed the base. Okay, so similar to last class, I'm trying to do a little bit more AP style questions with you. So if you notice, the next 5 questions on your notes are actually AP style multiple choice questions from section 2.4. And what we're going to do is kind of like last time. I'm going to have you work through these questions, but I'm actually going to go over them with you, unlike that worksheet from last time where I just gave you the answer checker. I have not written my thought processes down, but these questions are very similar to ones we've done previously on the notes. So what I want you to do is work with your table to answer these 5 multiple choice questions. I'm going to give you about 10 minutes, and after 10 minutes, we'll go over them. So see how many you can get an answer to in 10 minutes. Okay, let's chat. Number 1, if you follow the kind of process we were doing in the questions just above it, you'll see that this is 36 to, that's not a pointer, 36 to the x divided by 2 power, which I could rewrite as 36 to the 1/2 power raised to the x power. Well, 36 to the 1/2 is like saying square root of 36. What is the square root of 36? 6. So this is 6 to the x. We should have picked A. How do we do? Okay, fabulous. Number 2 says the function h is given by h of x equal to 5 times 3 to the negative x over 2. And I'm now realizing that that was a typo, which is why you couldn't answer it. This should have said, what is the value of h of negative 1? Okay, so let's pretend like that's what it said, and we'll do the problem together. Just kidding, not negative 1, 1. That's definitely on me, my bad. That should say a whole 1 right there. Typo. So if we're doing h of 1, that means we're going to take the 1 and we're going to plug it into the equation. This is 3 to the negative 1 over 2. Ooh, we just said this. Well, a couple questions ago. What do we do with negative exponents? Flip them to the bottom. Okay, then I have 3 to the 1/2 power in the bottom. What's another way to write something to the 1/2 power? Square root. So this is like 5 over the square root of 3. My bad. There's definitely a typo on there that kept you from answering the question. Sorry. Number 3 says, which of the following functions is an equivalent form of the function y equal to 9 to the 2x? Well, I see that 9 to the 2x can be rewritten as 9 squared raised to the x power. 9 squared is 81, so this is answer choice D. How do we do on that one? Fabulous. Number 4, which of the following functions is an equivalent form of the function 9 times 4 to the x power? Okay, here's some things I see. I see that these all have bases of 16. I somehow need to have them have bases of 4 so that I can actually compare and make them equivalent. Or I make my version have a base of 16. Okay. I'm going to start looking through here for one that's very similar, and I noticed that these two have the initial value of 9. So if I was a student taking these tests, I would start looking at these two answer choices since the initial value is 9. Not necessarily meaning I can eliminate the other two yet, but I want to stare at those first since they're more similar to the starting problem. If I look at these and I use that power property, this is like 16 to the 1/2 power raised to the x. And this one is like 16 to the 2nd power raised to the x. Anything to the 1/2 power is like the square root, which we've done like 3 times now. What's the square root of 16?
4.
Oh, what's the square root of 16? 4, yeah. Oh, look. That's the same kind of question. These would be worth considering if you had a plus or a minus in the exponent, because that's how we know we're changing that initial value or the vertical dilation. Otherwise, we are not changing the vertical dilation. Ooh, and then question number 5. I saw a lot of blanks when I was walking around. The function f is given by f of x equal to 2 to the x, and the function g is given by g of x equal to f of x divided by 8. For which of the following transformations is the graph of g the image of the graph of f? I know that it's very tempting to want to select this answer choice, but it's not right. The reason you wanted to select it is because you see vertical and 1/8. But vertical and 1/8 is my dilation. That's not a translation. Vertical translations are created by putting pluses or minuses behind the entire function, not dividing functions. So that's definitely not right. In which case, this one's also not right. So I see that my answer choices have to do with horizontal translations. Horizontal translations occur when you have pluses or minuses inside the function. So if I take this g of x function, which I know is 2 to the x divided by 8, is there a way I can rewrite this to where there's a plus or minus on the inside, meaning in the exponent? The correct answer is yes. If I notice that 8 is in the power family of 2, isn't 2 to the third power 8? Okay, well, what if I did this? What if I undid the negative exponent rule? Isn't that still 1/8? Well, then I have the power of a power, or product of a power property, which means I'm multiplying two things with the same base. I can just simply add their exponents. This right here is telling me that I'm going to translate it which direction, left or right. This should be answer choice B. So you're trying to get them to have similar bases so you can condense them down. That was a challenging question.